So basically, this is all about St Venant's principle. And I've got two confessions to make straight off the bat. The first off, I described this in the promo video as St Venant's theorem. And I guess for over 40 years, I've been under the misunderstanding there's a theorem and there's a principle. The theorem is actually quite complicated about torsion and circular shafts. The theorem is actually quite a kind of a loose thing. Sorry, the principle is quite a loose kind of definition, as we'll see a little bit later on. Also, the second thing is I do apologize to all French speakers. My pronunciation of, I'll try it once very carefully, St Venant. When I'm in a live class and there's somebody who's French speaker, somebody who's French, they always pulling me up on this, and I try and remember. So that's my best shot there. It will now degrade as we go into the presentation. So what is St Venant's principle all about? Well, the translation that I found is this, a lot of wordy stuff. The difference between the effects of two different but statically equivalent loads becomes very small at sufficiently large distances from a load. A, that's a real mouthful, and B, it doesn't really kind of tell us what, how can we use it? What's the principle behind it? And that's really what I want to kind of explore in this session. And again, these are just my ideas. You may have different ideas. Again, I really welcome any feedback, any, Tony, that was rubbish, that's wrong, I don't like that, oh, that's a good idea, whatever it is, please feel free. It's again, it's a discussion, perhaps more than kind of perhaps a teaching. So what it means is that I've got two plates here, and I'm applying a load at the far right-hand end. This one, I'm applying a point load, but my target region of stresses is over here where the yellow circle is. And basically what St Venant's theorem is saying is if the applied load is far enough, we don't care what the form of the loading is. Now they must have the same equilibrium at the center of the target there, so the forces and moments must be the same balance. So we have fundamentally the same load path, but basically we get this diffusion effect coming in. So the local stress state is insensitive to the form of loading, and that's something we really leap on with finite element analysis. And I'll try and show some examples of how we kind of take advantage of that kind of as we go through. So that's the idea. Let's actually put some stresses on there. Now here I'm looking at the stresses flowing in this plate in an axial direction, and what I've done is I've clipped the contours. I often do this in FE analysis. I don't want to have some crazy high number here and then everything else scaled down to that. So I've clipped everything at 1400 units, I'm going to call it. The loading I'm putting on is 1000 units. There's cross-section areas unity. So the nominal stress is 1000. Nominal stress is sort of this kind of mucky green color. So we're over here, we get the nominal stress. So this was our target region. We can see we've got diffusion back to the nominal stress at that point. Again, it's a bad idea to apply a point load, so this is something we wouldn't typically want to do in an analysis, but just really to show the point. And just to emphasize, this is a stress singularity. The stresses go off to very, very high levels here, which we'll kind of show shortly. One quick word about the boundary condition on the left-hand side. I've constrained here in the x direction in translation, and then all the rotations, but the y direction, I've only put the center line point constraint on, or a single node there. That allows free Poisson's ratio contraction, so I can get an even stress distribution. If I don't do that, then I grab this end, or grab the edge, and I get singularities popping up here and here. So just a little tip, if you want to emulate this, I want to repeat this kind of work, then that's just something you have to pay attention to. And here is the distributed loading now. So I've used this, and I've got to thank the folks at Siemens. They actually allow me to use their products here, FEMAP and NX Nastran, on a kind of a gratis basis as I do this, and various other solvers, other FEA companies do as well. So I would like to thank them for that. This is an even distribution of load applied here, so we're getting a good distribution of stress right on that edge there, so naturally there's no issues back in here. So basically, that is the bad news. This is the good news. This is the distributed load in here. So that's what we want to look at. Now I've played some variations on this. I've said, well, let's put corner loads on, or on the center load. So really trying to sort of emphasize the point that whatever happens in our target zone, it doesn't really care too much what the loading form is there on that right-hand edge. I've split the load here corner to corner. You can see the blue here, and the way I've chosen to represent the stress is that zero stress. So you can see that stress diffusion and stress flow. And I really like to think about stress flow. We can think of it as like a potential flow. And there are some analogies to fluid flow. It's like an airstream, not completely, but you know, at least we can begin to think of that. So sometimes I like to think of stresses as flowing. Now it's only the x component, but nevertheless it gives us some kind of idea here. We're getting two singularities. We're getting a diffusion length, which is again dominated by these two singularities at the corner there. And I carry on playing games. Now I split the loading into three, and now we've got three singularities, and the diffusion is still it's about the width of the plate, notice, that we get our diffusion length over there, and I'll come to that point in a minute. Now I put 3 points, there's 3 blips, 3 singularities. Now I've just split the load to a third across here, and again, a little bit of an aside, that's something that we wouldn't want to do, because what happens is that the edge stiffness, the element on the edge there, or node on the edge there, is only, if you like, connected to one element. In the middle, that node is connected to 2 elements, so it actually has twice the stiffness. So what we do there is we actually double the load in the middle, because we've got twice the stiffness, and we halve the load on the corners because we got half the stiffness. We can't really see it here, but if we actually put little point forces all the way across here, which is not a good idea, we would drop the load at the corners by half, and then we'd actually get back to a good distribution on that edge there. Little points which are coming out as a side, but again, they're useful to kind of pull out. So this is perhaps the bottom right is the best effort we can do with these point loads in here. But again, even then, that diffusion length has got a little bit better, a little bit shorter, but it's still about the order of the width of the plate. So we're playing around different types of application. Now I got a little bit more formal. What I've done is I've split this plate up. So this is the center load here. I want to know, well, I always think of a contour plot as being like a subjective plot. We can get the idea of what's going on. But I like to look at XY plots to get a more objective view of what's happening. So here, what I'm doing is to plot on the right-hand side here the stresses at different stations. So the pale green here, I've called it the edge, this is the singularity, and even with the very fine meshes I have in here, it just can't handle it. The numbers are crazy, and we go and we shoot off, and I can't remember what the peak value is here. It's probably about 30,000 PSI I'm quoting here rather than the nominal 1,000. So the blip in here is enormous. If I let that contour rip and get it to go to its maximum value, it would just be a red dot in there as we reach the singularity. We're not interested in that today. What we're going to say is, well, the edge there, we know it's ridiculous stress distribution. Come in 2 inches in, and that's about, this is actually 10 inches wide and I think 20 inches long. So we're coming at about this station here, and we can see, okay, now there's some semblance of a diffusion. But notice it's to 0 here, peaky in the middle, which is what we see through here. And the idea is that we get a diffusion length, and here the diffusion length is just around about 10 inches. So the gray dots across here are showing that 10 inches, so that's kind of equal width, kind of just about here. We can see a little bit of a variation if we look at the contour bands. We look at the plot across here, but it's headed towards the nominal stress of 1,000. And by the time we get here, there's a couple of contour flips, or there's one contour flip here as it kind of goes 9995 to 1005 maybe. But there's, to all intents and purposes, we've got a nice settled stress in here. So that characteristic length seems to be associated with the width of the plate in that particular case. So stress becomes more or less constant after that distance. And that's what St Venant, he can kind of quite pick up on a characteristic length, but we tend to notice that we have this idea of characteristic length. And that's something I really want to kind of jump on and talk about kind of as we go through here. So now I'm going to narrow the plate and see what happens. Well, as I narrow the plate, it's interesting. We still get the stress singularity here. But now, if I look to see again, there's the singularity on the edge, 2 inches in, 4 inches in, 6 inches in. By the time we get to 6 inches, it's smoothed out beautifully at that particular point. So again, this is now, the plate is 5 inches wide. So it's actually about 5 inches is where it settles down. Somewhere between 4 and 6 inches, we actually get a good diffusion settling down. So it seems to be telling us is that the trend is the plate width is related to the diffusion length. And we'll keep on looking at that as we come to the next slide. I've narrowed it even further. So now it's just, the width is just 2.5 inches. So we can see that the stress flow, and I've kept the nominal stress the same. I've reduced the load as I reduce the width. So I keep this 1,000 nominal. You can see with the cuts I've got, or the lines I've got, it's diffusion very quickly. So everything overlays on top of each other after around about sort of 2 inches. We see 4 inches and beyond is nicely sitting down on the 1,000 level. So the stress is constant after, again, what looks like a critical distance for this idea of St Venant's principle. It's something physical that we can perhaps pick up. We can use an engineering judgment call. It looks like it's actually the plate width in this particular case. And I think that was the last one that we do in the series there. So just some conclusions from the plate example. Point load is a bad idea, but I'm doing it here to show the principle in practice. Please don't. I'm always careful to say I'm using this as a demo, but don't do this at home. Basically, don't apply a point load. Bad news. The stress diffuses to a constant over a certain length of the plate, and so it looks like this diffusion on characteristic length is a function of the plate width. In this particular case, with this particular geometry, it's not a function of plate length. Now, why is this? Well, the edges of the plate act to align the stress locally in an axial direction. So as that plate gets narrower, the stress is already entrained to flow tangential or parallel to the edge of the plate. It's a little bit like fluid flow. If I've got a wind tunnel, and it's a very big wind tunnel, and I've got a small feature in there, then the air is kind of coming up to that feature and having to diffuse around it or move around it in quite an abrupt way. If I have a narrow wind tunnel, or the object is occupying a large amount of space, then the flow is entrained along the walls of the wind tunnel. So it's not a surprise. The flow is already moving parallel, and then it sees the object and it is going to change its direction a little bit. So that's why putting a large object in a narrow wind tunnel isn't a good idea, because you're not modeling free stream flow. So this is the idea. The narrower that plate gets, the more it's entraining, and it's actually keeping that critical plate length, the critical length to the plate width. So the narrower plate actually improves the stress flow. It diffuses to a constant level faster. We see that effect in the stress concentration factor calculation. If we've got a plate with a hole in it, then if it's an infinitely wide plate, we can say the stress concentration factor is 3. Actually, it's then we bring in a finite width plate. As that plate gets narrower and narrower, the stress concentration factor actually goes down, because it's exactly the same idea. We're constraining that stress to flow. Now, the counter to that in stress concentration factor is that as we narrow that, then the nominal stress goes up. So we've got stress concentration factor of 3 times perhaps a low stress, and then we have a stress concentration factor perhaps has dropped down to 1.5, but the nominal stress has gone up because our net section is bigger. But it's the same kind of idea, same kind of effect. So something to kind of think about. I like to think about stress flowing and the way that the stress flows. So stresses tend to diffuse to nominal values at distance from the local stress raises. That's or local loads, I should say, is the key thing that St Venant's picked up. But we can also say, obviously, the same thing if I constrained one edge as a point, then away from that constraint, same kind of idea. So loads and constraints are really what St Venant's talking about. He's actually talking about loads, but we can talk about constraints. But I can also extend it to local stress raises. We have a disruption of the stress flow in a local feature. As we move away from that, we get the same kind of effect. So St Venant didn't really talk about that. But I think common sense, we can apply the idea to stress raises. These are all generally known as St Venant's principle, and we kind of bandy this around, but it's all about this critical diffusion length and getting away from that region of local influence for different kind of purposes. Now, I've used one significant length in my particular case, and we can see that typically we would use 2 to 3 significant lengths. Now, what is that significant length or significant distance? It tends to be a geometric feature. Here we've got the width of the plate. We're going to see very shortly. We actually can look at the diameter of, say, a shaft. We're a little bit later on. We're also going to look at the length of a feature, or the distance of a notch, or length of a notch. So significant lengths can be geometric features such as widths or diameters, or they can be quite an abstract length. If you've got an unusual looking component and you're kind of working with that and variations on that, you might well become aware of some characteristic length which is a little bit more abstract, some geometric definition or dimension which is playing a role in your particular case. And as you get experience, you kind of jump on that and say, well, I know this is a key dimension in here. So that's basically the broad conclusions coming from that. Now here's an example. We're going to go to a shaft, and this is an awkward, very awkward piece of geometry that we came across, and it's a long needle-like shaft. And the trouble with it is, if I've got, say, a tip load which is bending this shaft in here, this needle, then to try and keep the aspect ratio maintained, I can only put a few elements in here because I'm wasting a huge amount of elements around here away from the region of interest. I'm assuming the region of interest is here, is here, is here. And I haven't got a very good mesh distribution through there. I just can't get the element count up if I want to keep the aspect ratio sensible. So I've got about a 1/4 of an inch diameter in that particular case, and that's of the major diameter at this joint. So that's this diameter over here. I'm using that as my call for the characteristic dimension. I could have used the narrow one, but this is, again, it's up to us. We're in control. We decide what we're going to use as this dimension here. Now, what I want to do is to say, let's get a local model. And what I'm going to do is chop out a section 1 inch upstream, 1 inch downstream from that particular section there. And I attack the boundary conditions this way. The left-hand boundary condition, I'm going to just apply a constraint to ground. The right-hand boundary condition, I'm going to use a rigid spider element, and this is a typical spider element here, and I'm going to transpose that load balance from that far point, bring the shear force to that point, and then the corresponding moment to that point as well. So I'm going to do a little short section. And the bottom picture here is the short section. And what I've done then is to say the spider gets the load in, both the moment and the shear force. Now, there's a couple of things going on here. If I constrain that left-hand end, it's over-constrained because I'm locking it down. I'm not allowing Poisson's ratio effect to naturally allow changing that cross-section. I'm locking it down at that particular point, as opposed to being locked down over here. So that's one issue, and that's, again, now our constraint boundary condition. Use St Venant's theorem to get far enough away from the region of interest. Similarly, with the loads being applied, well, again, I'm applying point loads, and I've got this rigid element. So I've got poor local stresses immediately in. I've used the term RBE2. It's a perfectly rigid element in here. It's a displacement relationship type of element. And the little perturbations or stresses in here, it'd be a bit of a mess if I looked locally in there. So I want to get a diffusion out. So my critical section over here doesn't know really where it's sitting. It sees the boundary conditions, it sees the influence we diffuse out. So just as a comparison, this is the full model, poor element distribution, just because the sheer number, I've zoomed in here. This is the actual complete model in here, and I can go to town more. I can use that element budget. Instead of wasting elements down here and down here, I can pump them in where I want to see the local elements. So a great application, really, of St Venant's principle. Now, I actually play a little bit of a game here, and I say, well, that's what I started off with. How tight can I make this? Because, again, element count is everything. So 4 diameters I'm using in here, so a factor of 4 on that dimension. I get very good relationship to just a simple calculation. The stress varies slightly because the mesh is changing in here. I didn't do a real convergent study on the mesh in here. It was more the nominal stress I was interested in, and the simple stress concentration. I then shortened it further. I get very similar stresses between these two. So going to, I've got to move my little picture out of the way, 2 diameters in that particular case, I'm still in good shape. Now I push this a little bit further, and 1 diameter, I'm starting to get the influence of the boundary condition here and the loading in here starting to influence the stress picture in here. So that 1 diameter in my particular case isn't enough. There's not enough diffusion length going on in here. So we can relate that back to the plate and everything else. We could do a real kind of study on the detail of the stresses in here. Come down to 1/2 a diameter, and I've really, I really messed it up. The influence of the loading, you can see the patterning in here. The boundary condition here is dominating the stress diffusion. The assumptions or the limitations of the rigid element here, again, the same kind of idea. So basically, I've really disturbed the local stress variation because I'm not kind of following the principles or the guidance of St Venant's principles. So again, you perhaps would have to explore this, get familiar with it, and once you've got some experience, then you'll have more idea of what kind of that critical length should be. This one is a little bit of a flyer here. I'm going to talk about geometry features. So this is a model I knocked up fairly, in fact, yesterday. So it's not kind of fully bottomed out. But the idea is that I want to have an I-beam, which is going to be representing a plate which is loaded in the middle and built in at both ends. Now, I've used a symmetry plane here to establish that. I've loaded the face here, and I fully fixed the end here. I didn't want to actually hardwire this to ground. I wanted to see some diffusion of the end in there. So that's the idea behind this little model here. So I've got a model which actually doesn't have a bracket and doesn't have a little, I'm assuming a fillet weld and a weld toe in there. This one here, if I can pick up my arrow, this one has a bracket or a gusset and also has a little weld toe in there. And this is a classic little problem, and when we're dealing with stress concentrations, particularly with welds and things like that. And the maritime certification authorities, DAS Nord Veritas, Lloyd's, and so on, they actually use this as a little case study to use what they call the hotspot approach, which is basically say, can we eliminate the local stress concentration there, because in a weld, it's a specific locked-in profile. I put a little radius in here. That's too locked in. We want to have a generic application. So what they do is they want to get rid of that stress concentration factor there, actually extrapolate the stresses through, and then say, well, with the nominal stress back in again, let's apply a stress concentration factor which we bring from our practice and our principles, rather than getting stuck with whatever that comes from FEA. So I've kind of jumped on this idea to say, well, we've got a sort of St Venant's principle idea here coming from the weld toe, but also from the bracket as well. As we move away from the bracket, maybe this beam doesn't care about the influence of the bracket. As we get closer in, maybe the stress distribution here doesn't care about the influence of the weld toe if we're far enough away. So to my mind, it's like an extension of St Venant's principle. Here are the stress and displacement results for the two. I've clipped the same at stress levels, which are stress levels which kind of characterize the bending at the center here. We've got peak bending here, then reversal of bending as we come down to the root, and we also have a stress concentration at the toe there. So that's basically the idea. So I'm going to drill down a little bit, see the difference between these two. And just a quick review, this is what DNV, ABS, Lloyd's hotspot methods kind of apply. And so there's my bracket, there's the weld toe. And what they're saying is there's a region 3 in this beam far enough away from the bracket where the stresses don't know anything about the bracket. They haven't got that stress diffusion influence yet from the bracket. So that's region 3 outside here. Region 2 starts to see the influence of the bracket, and it's only region 1 that starts to see the influence of the weld toe. So based on that, what they're saying is if we take the stresses which are present in region 3 and 2, and we want to get rid of the influence of the local disturbance of the weld toe, then we can extrapolate through, and we've actually extrapolated this region and then we get back to a nominal stress. So I kind of jumped on this idea. It's really like an application of St Venant's type of principle, where the disturbance is a geometric feature rather than a loading feature. So this is what I've come up with here. So this is the stresses now in the extreme fiber. So here we've got just to kind of remind ourselves, there's the end plate and there's the beam. And we're looking at stresses kind of running along there from left to right. So looking at the stresses, we get, this is the root bending moment here. This is without the gusset. So I get a root bending moment here, and then I get a tip bending moment here. Now, because it's constrained, it's basically a center section here, then we get actually a reversal of bending. So we get a reversal of the bending stresses. So if I draw the center line on here, that represents the extreme fiber stress top and bottom at that station due to the root bending, and the reversal of bending somewhere around here due to the center line. Now, with the bracket, it's kind of interesting. The bracket or the gusset actually, because of the way I've loaded this, it changes the bending moment down in here. So because actually we get the influence of the gusset there, the actual line of action of the bending moment coming out here, the loads coming out here, puts a slightly different bending distribution into the beam. So I can't quite compare apples with apples there, but nevertheless, if I take that account into effect, you can still see the same kind of idea. So yes, we get a slightly more different bending distribution. So the root bending is slightly different, and the center section bending moment is slightly different. Hence, the stress levels change slightly. But nevertheless, we can see a couple of things going on here. This is the local gusset influence. So this stresses here are happily coming down under the boundary conditions implied by the bending moment, the root bending moment, and the center section bending moment here. And then you can see this kind of at the top and the bottom, this global change in stress is the gusset influence. So yes, there's like a St Venant's principle effect, and it's a little bit longer than the gusset length. It extends a little bit forward. This is the gusset length because there's the weld toe there. So about maybe 1.5 to 2 times the length of the bracket. Away from that, the beam doesn't care. There's no local stress influence on there. The blip here is the local stress raise of the weld toe, and this is where we get our particular, it's not a singularity, it actually would be a converged stress as long as I did a good job in here. You see that's the stress concentration factor. It's about a factor of 3 in there, just eyeballing it. So that is very much a local kind of influence. So again, it's kind of summarizing the way that the DNV and the ABS and Lloyd's Register are kind of thinking about things. It's a local disturbance. So again, I think it's a useful interpretation of St Venant's theorem there. So in summary, the St Venant's principle describes stress diffusion due to loading. That's the fundamental principle. But we can extend that to constraints, but also to geometric features, which I think is interesting. The bracket influence zone is the same order as the bracket length, maybe 1.5, maybe 2 times it. The weld influence zone is actually very much the same as the weld toe width. So there's very local disturbance over there. So I kind of put that out as just some general thoughts and some general observations. So we looked at the definition of St Venant's principle, extended it to constraints as well as loadings, and then a bit more unusually, I think I've also said it can be applied to geometric features. So again, I'm interested to see what experience you guys have with that, any recommendations, any favorite methods, any kind of comments, albeit criticisms or whatever it might be. During my 12 years of doing e-learning, I've learned to have a very thick skin, and if you disagree with some of the comments and ideas and so on, then it all adds to the discussion. So I think just as a closing note, thanks very much from my side for watching this. We're going to be getting into Q&A now. I just run over slightly the half hour. And just a little bit of a heads up for the next session. That's going to be talking about FEA sanity checks, and basically we don't make sure we don't fall into the garbage in, garbage out. But I won't be talking about full kind of project checking. What I'm very interested in is those quick checks within about 5 minutes of seeing the results coming out the model, Are we on the right ballpark? Is the model rubbish? Do we stop at that point and redo it? Heading off here, the idea that I don't want to spend, say, 2 days post-processing and producing a report on results which are rubbish, and I could have headed that out early on.